Calculate the pH and the equilibrium concentrations of a 0.025 molar formic acid solution. The chemical formula of formic acid is given here, and what this is to show you is that one of these hydrogen atoms is acidic. So we can use just the generic HA is going to decompose into H plus and A minus. Now initially, we have a concentration of 0.025 molar for my acid, and I have no H plus and no A minus, but I'm going to change by some amount X. So the reactants are going to decrease and the products are going to increase by that amount X. So that at equilibrium, my HA concentration is 0.025 minus X, where the concentrations of my H and my A minus are both X. Now I can put this into the K expression. So the Ka has a value. That value is 1.8 times 10 to the negative fourth, and that is going to be equal to the concentration of the hydrogen ion times the concentration of the conjugate base, the A minus, all divided by the concentration of the HA, and these are equilibrium concentrations. Now the equilibrium concentrations are represented by the E row of the ICE table. So I'm going to fill that in for my concentrations. So we have X times X divided by 0.025 minus X. Now because my initial concentration is less than 1,000 times different than my K value, I cannot just simplify. I need to go through and do the entire quadratic. So I start by multiplying both sides by what's in my denominator on the right side. So 1.8 times 10 to the negative fourth times a 0.025, I get a 4.5 times 10 to the negative 6 minus 1.8 times 10 to the negative 4x, and that's going to be equal to x squared. Now, in order to use the quadratic equation, I need to set this all equal to 0. So to do that, I'm going to move what's on the left side of my equation here to the right side so that I have x squared plus 1.8 times 10 to the negative 4x minus 4.5 times 10 to the negative 6. Now, in my classes, you should be able to access a quadratic equation solver through the Responda's Lockdown browser. If you would prefer to work out the quadratic on your own, the quadratic equation is that x equals b plus or minus the square root of b squared minus 4ac all over 2a. So the coefficient in front of x squared is a. The coefficient in front of x is b. And the coefficient in front, or the constant, I should say, is C. So that is how you fill in, that's the wrong color, that is how you fill in the quadratic equation. Now I used the quadratic equation solver and I got two roots. I have an x equals 0.00203 and I have an x equal to a negative 0.002213. So which root do you use? Well, you can't have a negative concentration. You see, my x value is going to be equal to the concentration of my hydrogen ion, and I can't have a negative value, so I'm not going to use the negative answer. It's only the positive answer. And as I mentioned, that x value is equal to the concentration of my hydrogen ion as well as my conjugate base. Now, the question was looking for equilibrium concentrations as well as the pH. So the concentration of the hydrogen ion is going to be equal to the A minus, which is also going to be 0.00203 capital M molar. Now that A minus is going to be the conjugate base here, so the formate ion. The concentration of my weak acid is going to be, and I use this equation here, 0.025 minus X, and I get a concentration approximately equal to 0.023 capital M molar. That doesn't completely answer the question because I do need to get that pH. Now, pH is found by taking the negative log log of the concentration of the hydrogen ion. We just said the concentration of the hydrogen ion is this value here, so I plug that into my calculator, and I get a pH value of 2.69. For the next problem, again, we're going to do the same operation, but with a different acid and a different Ka. So here I have my weak acid is going to dissociate into hydrogen ions and conjugate base. Initially, I have 0.10, but I have none of my products, and that value will change, and it will change by this value x that I don't know yet. The equilibrium concentration, 0.10 minus x, x, and x. I can put that into the K expression, and the K expression is going to be equal to the concentration of the hydrogen ion times the concentration of the conjugate base, all over the concentration of the weak acid, and that is at equilibrium. And at equilibrium, that is equal to 4.0 times 10 to the negative 4th. I plug in what I have in my row, my equilibrium row, and I have x squared at the top because x times x is x squared. And then I have 0.10 minus x on the bottom. Now, this is one of those that's right on the edge of can I simplify or not. When in doubt, don't simplify, work through the quadratic. So multiply both sides by the denominator here. You should get 4.0 times 10 to the negative 5 minus 4.0 times 10 to the negative 4x, and that is equal to x squared. Again, to use the quadratic, we need everything on one side so that we're equal to 0. So this is what the quadratic should look like before you put it in the solver or use the quadratic equation. Now, when I put it in the solver, I get an x value of 0.00613 capital M molar. But what does that x mean? Well, that x is the concentration of my hydrogen ion, but it is also the concentration of my conjugate base, which in this case is the nitrite ion. So the concentration of my weak acid, my HNO2, is going to be equal to my initial value, 0.10, minus this value of x, 0.00613. And that is approximately equal to 0.10 capital M molar. So it is entirely likely that we could have simplified that one. Now, we haven't finished the question, however, we need to calculate the pH. So the pH is going to be the negative log log of the concentration of the hydrogen ion. The hydrogen ion is given to you right here. So we take the pH of that value, the negative log value, and I get a pH is 2.21. We're going to shift gears a little bit, and we're going to look at one that tells us a percent dissociation. So you need to remember that percent dissociation is going to be equal to 100 times the ratio of the concentration of the weak acid over, the concentration of the hydrogen ion over the concentration of the weak acid. So knowing this, we can calculate this concentration of the hydrogen ion and therefore end up with the Ka. So the dissociation, percent dissociation is 3.0%. That's going to be equal to 100 times the concentration of the hydrogen ion that we don't know over the concentration of the weak acid, which we were told. We do our algebra here, so divide both sides by 100, multiply both sides by 0.15, and get a concentration of the hydrogen ion that is equal to 0.0045 molar. But what does that do for us? Well, we have a weak acid, and it should have told you monoprotic, because no reason to get difficult with this. So we have our weak acid, and that will dissociate into our hydrogen and conjugate base. We know we have some initial value. We know it's going to change by some value x that we don't know, and that these will be the equilibrium values. Well, now we know the concentration of the hydrogen ion. So this is actually the x, the change that we're going to note here. So in order to calculate the Ka, then I'm going to solve for all of my equilibrium concentrations. and then calculate that value. So the concentration of H, I already solved for, and that's equivalent to the concentration of A minus. So the concentration of my weak acid is going to be 0.15 minus this value. So you should get 0.1455. And I'm not going to round that right now in order to eliminate rounding error. So the Ka expression is going to be the concentration of the hydrogen ion times the concentration of the conjugate base, all divided by the concentration of the weak acid, and all of that at equilibrium. So now I have these values, and I'm going to plug them in and solve. So when I solve this, I end up with a value of 1.39 times 10 to the negative 4, which we would round to 1.4 times 10 to the negative 4. We would round to two significant digits because our question gave us two significant digits, both in the molarity as well as the percent dissociated. For the next one, the pH of a solution of cyanic acid is 2.77. Calculate the Ka of this acid at this temperature. Okay, so in this case, we have a pH. Here we're going to start with the pH. pH is the negative log of the concentration of the hydrogen ion, and this is going to be at equilibrium. So I'm told the pH is 2.77. I can back calculate for that concentration of hydrogen ion. And I do that by taking the negative or anti-log, not negative, the anti-log of this value, this negative 2.77. I'm getting ahead of myself here. Now in my calculator, that is a shift and then the LOG button. It may have like a 10 and a box or 10 to the X, or you could just do it the old-fashioned way and type in 10 and then use your caret negative 2.77. All of those methods should give you the same answer, which should be 1.70 times 10 to the negative third, and that is equal to the concentration of the hydrogen ion. But we aren't nearly done yet. Now that is the concentration at equilibrium. This is a monoprotic acid, so we can just use our generic HA. So at equilibrium, the concentration of the H is going to be equal to the concentration of the A minus. So I have those concentrations. They are the same. But what about the HA? Well, it starts with a 0.0100 solution, and it's going to be changed by some amount X. That amount X is also equal to the concentration of the H ion. So I'm going to subtract my 0.00170 because these numbers are the same. So that at equilibrium, I have a weak acid concentration of 8.30 times 10 to the negative 3. So to calculate the Ka, you need to recognize how that Ka comes together. So it's the concentration of the hydrogen ion times the concentration of the weak base divided by the concentration of the, I said weak base, hydrogen ion times the conjugate base divided by the weak acid. So I'm going to fill in the numbers that I know. And solve, and I get 3.48 times 10 to the negative 4. I have 3 significant digits here and here. I'd keep 3 significant digits. Close enough. For the next one, we're going to be working with an aspirin tablet. So if we have 325 milligrams, then that means we have 0.325 grams. Calculate the pH of a solution that is prepared by dissolving 2 of these tablets in 1 cup of water. Well, if I have 2 of these, then 0.325 times 2, that means I have 0.650 grams of acetyl salicylic acid. I need to convert that into moles. 99% of the time when you see grams, you need to convert it into moles in my class. So you need the molar mass. And 1 mole of ASA, and the chemical formula is given to you here even if it's not formatted properly, I get 180.17 grams per mole. Now, I'm going to just take that a step further and let my calculator do the work and divide that by the volume. So it says 1 cup of water. 1 cup of water is 237 milliliters. So I convert that into liters. And I get a molarity or a concentration of 0.0152 capital M molar of ASA. So that's what I'm starting with. Now the question asks me to calculate the pH of this solution. And I have a Ka value. So this is going to be my initial. So I have my HA, my H plus, and my A minus. Initially, I start with 0.0152 capital M molar. I'm going to change by some value, X, that I don't know yet. And then at equilibrium, my concentration of HA will be 0.0152 minus X. Concentration of H will be X. Concentration of A minus will also be X. So my Ka has a value, and that value is 3.3 times 10 to the negative 4. And that's going to be equal to the concentration of my H, concentration times the concentration of my A, minus divided by the concentration of my HA, all at equilibrium. Now, this is one of those that you cannot simplify, and you can't simplify it because of that rule of 1,000. The initial concentration is not 1,000 times different than the Ka value. So we cannot simplify this. I need to multiply both sides by the denominator. And when I do that, I'm looking for my notes, I get 5.016 times 10 to the negative 6 minus 3.3 times 10 to the negative 4x, and all that will be equal to x squared. In order to use the quadratic equation solver, or the quadratic equation for that matter, you need to get all of your pieces on one side so that it all equals 0. So 0 equals x squared plus 3.3 times 10 to the negative 4x minus 5.016 times 10 to the negative 6. Now, when I put that in the quadratic equation solver, I get one positive root. So x is equal to 0.00208 capital M molar. Now, this x is going to be equal to the concentration of my hydrogen ion at equilibrium, because that's how I have to find it. The question is, what is the pH? So I need to take this value, recognize that the pH is the negative log log of the concentration of the hydrogen ion, plug in 0.0028 into my calculator, and I get a pH value is equal to 2.68 for that solution. And finally, we have a challenge problem. Now, in my notes, I have one answer, and then I calculated it this morning, and I got another one. So we're going to give it a try. So we're going to start with 2.14 grams of sodium hypoiodite. Sodium hypoiodite is NaIO. That is sodium hypoiodite. So 2.14 grams of this substance is made into a solution. Well, 99% of the times you see grams, you need to convert it into moles. The molar mass of this substance is 143.89 grams. So I have 0.0149 moles of this substance. Okay. Now, I'm told that it's dissolved in water in order to make 1.25 liters. So I can convert this into a molarity, into a concentration, by dividing it by 1.25. And I get a concentration of 0.01190 capital M molar. Now, the question asks us to find the Kb for this. We're given a pH. So if I have a pH, well, I'm going to write out this first. So if I have sodium hypoiodite and I'm going to put that in water, we're going to have some sort of a reaction. And that reaction is a double displacement. Remember, that takes one of these cations and pairs it with this anion. So I have an HIO. That's a weak acid. And then I have the other product, which is going to be sodium hydroxide. And that's a strong base. So we have a weak acid and a strong base on my product side. Now, this is a Kb expression. Kb. So I have this HB, and I have the OH, and I have the original base. So initially, I start with 0.01190 moles of this business, and it's going to change by some amount X, which is going to increase each of these products by some amount X, so that at equilibrium, because I am making an ice table, I should have 0.01190 minus X of my sodium iodide, and I should have the amount X of both my base and my weak acid, which is really what it is. Now I'm told that the solution pH is 11.32. I need to use that because that's actually going to tell me this value here. So there are a couple of different ways you can go about solving for what is the concentration of the hydroxide ion, because that's really what we're looking for here. So how do I get hydroxide ion from pH? Well, you could take 14 minus the pH and get the pOH and calculate the hydroxide ion from there, because the pOH is equal to the negative log log of the concentration of the hydroxide ion. You could do it that way. That's probably the most direct way. Or you could take the pH and solve for the hydrogen ion, and then solve for the concentration of the hydroxide ion by taking the Kw, 1 times 10 to the negative 14, and dividing it by the concentration of the hydrogen ion. So whichever way you choose, you should end up with the same answer. And that should lead you to a concentration of the hydroxide ion being 2.09 times 10 to the negative third, capital M, molar. So X is equal to the concentration of the hydroxide ion, which is 2.09 times 10 to the negative third. Well, that's also this concentration. And then at equilibrium, the concentration of my NaIO is going to be equal to 0.01190 minus my X value, 2.09 times 10 to the negative third. And I get a value of, see, it looks like 9.81 times 10 to the negative third. My own writing is a little bit scratchy there, so it's hard to tell. So the Kb we can calculate, and that's going to be the concentration of the hydroxide ion times the concentration of the hypoiodic acid, 2.09 times 10 to the negative third, all divided by my initial base at equilibrium concentration. Now, when I do this calculation today, I get 4.44 times 10 to the negative 4. In my notes, I have 5.44 times 10 to the negative 4, and I can't figure out how to make that 5. So if you can figure it out, please send me your work and let me see what you've done. If you can figure out what I've done wrong, I'd love to hear about it.